talk, Vimala is going to tell us about how to verify replication-aware linearizability.
Good evening, everyone. I am Vimala, a PhD student at IIT Madras. Today I will be presenting our work on automatically verifying replication-aware linearizability. This is a joint work with Kartik, Nagar, Aseem, Rastogi and Sivaramakrishnan. So, modern cloud-based software services replicate data across multiple geographically distributed locations to improve fault tolerance, reduce latency and ensure availability. This is especially important in collaborative tools like Google Docs when multiple users can concurrently edit the same document. These services rely on centralized servers to resolve conflicts and to maintain consistency across replicas. However, there is growing shift towards decentralized systems seen in platforms like GitHub. Here each user has a full copy of data and changes are synchronized peer-to-peer. This local first model brings in benefits like better security, privacy and user ownership of data. But how do we build systems like this? The answer is to embed replication into the data type. We designed the system from the ground up to support multiple divergent copies that can be merged later. Recently, mergeable replicated data types or MRDTs have emerged as a systematic approach to embed replication into the data types. So, any sequential data type with a three-way merge function becomes an MRDT. So, this three-way merge function is a ternary function that takes as input the two versions that needs to be merged and the lowest common ancestor, which is the most recent version from which the two versions diverged. This function is used to reconcile the divergent states that has occurred at multiple replicas. For example, let us take an example of an add-win set MRDT. So, this MRDT supports three operations, that is you can add an element to the set, remove an element from the set and read the set. The three-way merge function for this MRDT is given here. So, it takes as input the LCA and the two version that needs to be merged and it computes the union of the intersection of the elements at the LCA and the two versions. So, this is basically this set contains the unchanged elements, that is the elements that were not deleted and unmodified. And then this V1 minus LCA and V2 minus LCA are the newly added elements to the set. So, this is how we implement the three-way merge function. So, let us take one example. For instance, let us take that there is one replica that starts with an empty set and then we fork off replica 2 from this replica 1 and then we apply two operations, add operations. So, replica 1 adds A to the set with the timestamp 1 and replica 2 adds B with timestamp 2. So, the states becomes A comma 1 and B comma 2 and now when replica 2 merges with 1, the resultant set contains A and B. But are we sure that this merge function is correct, and if so, how do we automatically verify it? So, given an implementation of a MRDT, we need a way to define the expected behavior, so we can check whether an implementation conforms to the expected behavior. A natural way to specify this behavior is by explaining the outcome of the concurrent execution in terms of linearization, that is sequential ordering of operations that are consistent with what the replica has observed. So, given an execution graph like this, the key question is, can we prove that the state sigma 7 and sigma 8 are same as the state we would get by applying a valid linearization of operations seen by the replica from the starting state. So, replication-aware linearizability is a correctness criterion used in CRDTs. So, the main idea here is that it requires all replicas to have a state which can be obtained by linearizing the update operations visible to the replica according to the sequential specification, and this linearization must respect the visibility relation, but there is no need for real-time constraints unlike classical linearizability. So, in our work NEEM, we adapt RA linearizability to the MRDT system model and introduce a simple specification framework based on conflict resolution policies of concurrent update operations. Then we propose a sound verification technique for proving the RA linearizability. At the core of this is a technique called bottom-up linearization, which uses some simple algebraic properties of merge function to show that it produces a valid linearization. We then design an induction scheme to automatically verify the required algebraic properties and generate a set of verification conditions and prove it in the STAR programming language. So, first let us see what an MRDT developer has to provide to our framework. So, a developer has to provide an MRDT implementation, which is the MRDT state, the set of supported operations and the three-way merge function. And the important thing to note is that not all operations commute with each other. For example, in the add-win set that we saw earlier, the add and the remove operations of the same element does not commute with each other. So, while generating the linearization, we need a deterministic way to resolve the conflicts. So, if these operations have to occur sequentially, in what order they would occur. So, in the case of advent semantics, the conflict resolution policy ensures that the remove comes before the add of the same element to preserve the advent semantics. So, given an MRDT implementation in the conflict resolution policy, let us see how we prove array linearizability. The proof is straightforward if there is only a single replica where all update operation happens because there is no interleaving of operations. The complexity arises when updates occur concurrently at multiple replicas, and the key challenge now is to show that the merge function produces a state that corresponds to the valid linearization of update operation that are seen by both the replicas. To address this, we introduce a technique called bottom up linearization, which uses some simple algebraic properties to produce the correct linearization. So, the 5 rules given on the right hand side are used to construct the linearization of operations. The core idea is to identify one event, apply to the argument of the merge on the left hand side of the consequent, extract that event out by removing it from the argument and instead apply it to the result of the merge. And the premises of this rule specify the condition under which this extraction needs to be done. So, let us walk through how we build the linearization for the sample execution. So, here event E1 and E2 are 2 local conflicting events, and according to the conflict resolution policy, E1 should be ordered before E2. So, we apply the bottom up 2-op rule and we peel off E2 from the argument, and now we have to prove this. Now, only E1 remains on replica 1, and then now we can apply the bottom up 1-op rule and then peel off event E1. Now, only LCA events remain, and now we can apply the merge idempotence to obtain the correct linearization. While we have identified sufficient conditions to show array linearizability, proving these conditions for arbitrary MRDTs is not straightforward, because the rules that I showed earlier has universal quantification on the MRDT states. We need to show these properties only for feasible state that might arise during an actual execution. To make this more concrete, consider the same execution except that the state at the LCA contains a comma 2. So, if the replica 2 attempts to add the element a with the same timestamp, we get the same state. The linearization order remains the same as that of the previous example, but if you see that the left hand side is not equal to the right hand side. This scenario occurs because if the LCA had the tuple a comma 2, there must have been an add event that added the element a with timestamp 2. And now the replica 2 cannot add the another event with the same timestamp, as timestamps are unique across all events. But such arguments are hard to infer and would change across different MRDTs. So, these the values of this L, A and B are not feasible in actual execution, but we need to consider only feasible states for proving. So, now we characterize these feasible states by sequence of MRDT update operations, and we do induction on these sequences to establish this property. How do we apply this induction? So, the merge function takes 3 inputs, sigma t and sigma 1 and sigma 2, and this pi t is the sequence of event that applied on the initial state gives the state of the LCA. So, we apply the induction on this sequence pi t, and the base case, so we have this base case and the inductive case. So, base case is easy to prove because it contains only the sigma naught, which is the initial state, which is an empty set, and it is easy to prove the property. For the inductive case, we assume that the property holds for some LCA state sigma t, and we aim to prove that this property still holds even after applying one more update event. This step can be automatically verified using the fact that the events E1, E2 and E3 all have different timestamps, and the inductive hypothesis helps us to prove the consequent. So, this proves this completes the proof of bottom up 2-op rule. A similar inductive argument is used to prove the properties about the feasible state sigma 1 and sigma 2 also. So, finally, we prove a theorem that states that any MRDT that satisfies the required algebraic properties are array linearizable. And we also show that if an MRDT is array linearizable, then the query results match what we would have got by applying the linearization of update operation visible to that query operation when applied to the initial state. So, we have implemented our verification technique in the F-star programming language, and we have verified several MRDTs. And our F-star framework includes an interface that defines the required signature for the MRDT implementation, and the VZs are encoded as F-star lemmas. And all that the MRDT developer has to do is that he has to provide he has to implement the MRDT code and use F-star to prove these lemmas. Once these lemmas are proven, our meta theory guarantees that the MRDT is RA linearizable. So, some of the MRDTs we verified are from the previous work or translations of known MRDTs. We have also created some new MRDT, verified new MRDT implementation that are marked with a star. And the second column in the table gives the conflict resolution policies we have used for the MRDTs, and this column gives the lines of code. The last column shows the verification time. During verification, we also found bugs in the earlier verified implementation, which we fixed in our work. So, NEEM also supports verification of state-based CRDTs. And our code is available in this following GitHub repo. Yeah, thank you.
So next speaker, come forward to get yourself wired up while we line for questions. Yes.
2 questions. Did you experience any difference when verifying with your method, your approach, MRDTs and state-based CRDTs, because they come with some more guarantees?
Yeah. So, MRDT is a kind of state-based CRDT. So, in state-based CRDT, since it follows a lattice model, so we need to prove only the 3 properties like associativity, idempotence and commutativity. But MRDT system model is much more complex because it contains the least common ancestor, and more complexities arises when there are intermediate merges, and also it's like bit more difficult.
And any comparison to other work that has the goal of verifying CRDTs? Maybe this is more focused on CRDTs and yours is broader scope with MRDTs, am I right?
Focus on the previous work is, there are other verification work in MRDTs that uses declarative specification which are not automated, like it requires manual proof effort. So, in our work we have made the entire verification process automated. So, the developer need not do any extra effort to verify their implementations.
Okay, thank you. We have time for more questions. So, can you go to the previous slide briefly? So when you say you verify implementation, you meant you re-implement in F star, verify in F star.
So we implement it in the F star. The implementation itself is in the F star programming language, and the VZs are also encoded in the F star.
So the real implementation could be in a different language.
Yeah, so we can extract the OCaml code out of the verified implementation and use it in distributed systems like.
So now you have this anybody else? So you have this RC policy.
Yeah.
So how did this impact your verification time or make the verification harder or easier?
So this RC policy are like MRDT specific, like you define based on the semantics of the data type, you define the RC policy. And the verification time is not based on the RC policy, it basically depends on the complexity of the implementation. So, I do not think it depends on the RC policy, but on the how complex the implementation is. If it is a complex implementation, its verification time is large.
So for inductive proofs, that's also done automatically? You don't need to put in any inductive invariants?
No inductive. Everything is taken care by the meta theory, and we have a set of VCs that are generated which are automatically verified in F star.